In this video, I'm going to go through how we can make use of the binomial theorem to help us solve congruence relations. So I've got the result over here on the right that we're allowed to quote. The fact that a plus b to the power of p is congruent to a to the power of p plus b to the power of p mod p, where p is prime. So let's have a look at the congruence relation I'm being asked to solve. So it says solve x plus 2 to the power of 3 is congruent to 1 mod 3. Okay, so what this is asking is which values for x could we substitute into here and do the calculation x plus 2 to the power of 3 and get a remainder of 1 when we divide by 3. Now I've got a bracket raised to a power, so straight away I'm thinking I might need to make use of the binomial theorem. So let's just check whether we can use the result circled in red on the right, and to do that check we have to consider the power of our bracket. Okay, is it prime? Yes it is, 3 is prime. And is it the same as our mod? Yes it is. So therefore we can make use of the result circled in red. So if we have x plus 2 to the power of 3, we can rewrite that in mod 3 as x to the power of 3 plus 2 to the power of 3. And then we can write in the rest of our statement, so congruent to 1 mod 3. And what I would say is using the binomial theorem, since 3 is prime, as we can only use it if our power and our mod is prime. Now on the left hand side I have the two terms raised to the power of 3, and 3 is of course prime and it's the same as our mod. So we can also consider whether we can use Fermat's little theorem, and what we can say using Fermat's little theorem is that the x cubed in mod 3 is congruent to x, and the 2 cubed in mod 3 is congruent to 2. And then I can write in the rest of my statement, which is 1 mod 3, and I'm going to say using Fermat's little theorem. Now our congruence relation is looking a lot more straightforward to solve. I just need to get the x on its own. So I'm going to subtract 2 from both sides. So we get x is congruent to negative 1 mod 3. And then usually we give our answer as the least positive residue. Okay, the negative 1, what we can do is add our mod 3 onto it so that we get x is congruent to 2 mod 3. And that would be my final answer. Let's have a look at another question. So here's our next congruence relation, and once again I have a binomial 3x plus 2 raised to a power which is 5, and it's congruent to 4 mod 5. Okay, so the power of our bracket is once again a prime number and it matches our mod. Therefore we can make use of the result on the right here, which links to the binomial theorem. What I can do is go to the left hand side of my congruence relation and rewrite it. I can take the 3x and we'd raise it to the power of our bracket, which is 5, and then plus the 2 also raised to the power of 5, and we can say that's congruent to 4 mod 5. And I'd say using the binomial theorem, since 5 is prime. Then we've got our two terms raised to a power on the left hand side. The power is prime, it's 5, it matches our mod, so we can make use of Fermat's little theorem. We could say the 3x raised to the power of 5 is just congruent to 3x in mod 5, and then the 2 raised to the power of 5 is just congruent to 2 in mod 5. So therefore the 3x plus 2 is congruent to 4 mod 5. And that is using Fermat's little theorem. Now our congruence relation is a linear one, so let's get the x term on its own. So I'm going to subtract 2 from both sides. So we get 3x is congruent to 2 mod 5. Now we've got it in the format ax is congruent to b mod n. So let's just check whether we have a unique solution. So we're going to do the highest common factor of the 3 and our mod 5. And of course that is equal to 1. So that implies there is a unique solution. So now what I need to consider is what do I need to multiply the 3 by, the value multiplying x, to make it 1 more than a multiple of our mod, which is 5. Well, if we multiply by 2, we get 6, which is 1 more than a multiple of 5. So I'm going to multiply by 2 on both sides of my congruence relation. So we get 6x is congruent to 4 mod 5. And since the 6 is 1 more than a multiple of 5, we can reduce it down to a 1. So we get 1x is congruent to 4 mod 5. And that would be my final solution to the original congruence relation.